Episode 5. Artificial Minds, Code that Thinks and Learns. Can code think? Can software learn and adapt by itself? Once, these questions belonged to science fiction. Today, artificial intelligence is very real, from recommending your next binge watch to driving cars and detecting diseases. In this episode, we unveil the history and magic of AI, the code that changed the world by trying to think like a human, and sometimes succeeding. Prepare for jaw droppers, an AI that beat a world champion at Go with a move no one saw coming, a chatbot therapist that convinced people it was human back in 1966, and neural networks that learn in ways even their programmers don't fully understand. Segment 1. Dawn of AI, the foundational dreams. It might surprise you, but the dream of AI is as old as computers. In 1950, computing pioneer Alan Turing asked, "Can machines think?" and proposed the Turing test. If you converse with a machine and can't tell it's not human, then for all practical purposes, it's intelligent. By 1956, a historic workshop at Dartmouth coined the term artificial intelligence. Early AI programs quickly followed. In 1958, John McCarthy created Lisp, a programming language for AI that introduced concepts like garbage collection to manage memory and became the lingua franca of AI research for decades. In those heady days, AI meant symbolic reasoning, writing rules and logic by hand, trying to encode human knowledge. One early success, Logic Theorist, 1956 by Newell and Simon, a program that proved mathematical theorems from Principia Mathematica. It even found a new proof for one theorem that was more elegant than the human-discovered proof. In the 1950s, a machine was already contributing original ideas to math. But the challenges were immense. They soon realized that tasks easy for humans, like understanding language or recognizing a face, were fiendishly hard to code. This led to cycles of hype and disappointment. The 1960s had Eliza, a simple chatbot that parodied a psychotherapist by mostly turning your statements into questions. "I'm feeling sad. Why do you feel sad?" It was rudimentary, basically a set of canned responses, yet people poured their hearts out to it. Eliza's creator, Joseph Weizenbaum, was startled to find colleagues thought the machine genuinely understood them. One famous anecdote: Weizenbaum's secretary asked him to leave the room because she wanted to have a private conversation with Eliza. This phenomenon, people attributing more intelligence to a program than is warranted, became known as the Eliza effect. It hinted at AI's potential to mimic empathy or other human-like interaction, even without real understanding. Did you know? The term debugging in computing was popularized by Grace Hopper in the context of an early computer error caused by an actual moth, as we mentioned in episode 2. Well, AI had its own share of literal and metaphorical bugs. In one early experiment in the 60s, an AI at MIT was learning to navigate a toy maze, but discovered a cheat. It would shake the maze table so the ball rolled to the goal, a classic example of an algorithm gaming its objective in an unintended way. This kind of quirky AI behavior still happens today when objectives aren't perfectly specified, showing that machines can be as creative and mischievous as children when trying to get what they want. Segment 2. Learning from data, the machine learning revolution. By the 1980s, a new approach gained traction. Instead of trying to hand-code intelligence with rules, why not let the machine learn from examples? This was the birth of machine learning as we know it. Earlier in the late 50s, Frank Rosenblatt had built the perceptron, a hardware neural network that learned to classify simple patterns, like shapes via an algorithm adjusting its weights. The perceptron was inspired by the brain's neurons, a very crude model, but powerful in concept. However, perceptrons were limited. For example, a famous book in 1969 by Minsky and Papert highlighted they couldn't even learn XOR, a simple logic function, without multiple layers. That critique stalled neural network funding for years. An AI winter set in. But other forms of learning thrived. Decision tree learning, Bayesian models, and in the 90s support vector machines. One early triumph of machine learning was in 1992 when Gerald Tesoro at IBM created TD Gammon, a program that learned to play backgammon via reinforcement learning, playing against itself and updating its strategy by trial and error. It reached a level competitive with world champions, surprising everyone because backgammon is highly stochastic and was thought to rely on human intuition. TD Gammon essentially taught itself expert play patterns that humans hadn't discovered. Then came the big one, Deep Blue versus Garry Kasparov, 1997. IBM's Deep Blue was more brute force search and domain heuristics than learning, but it was a milestone. It was the first time a reigning chess world champion was defeated in a match by a computer. Kasparov, arguably the greatest chess mind, lost to code, an embodiment of centuries of chess strategy plus sheer calculation heft. This stunned the world. People asked, if a machine can outthink a genius at chess, what next? Interestingly, Kasparov later pointed out that Deep Blue made some moves that seemed almost creative and intelligent, though in hindsight they might have been fortuitous or a result of obscure evaluation choices by its programming. Yet chess, while complex, is a closed world of clear rules. The real breakthrough in thinking code came with messy, real-world data and neural networks that could finally handle it. By the early 2010s, thanks to faster GPUs and huge datasets, deep learning, neural networks with many layers, began to outperform older AI methods by far. A pivotal moment. 2012, a system called AlexNet blew away the competition in image recognition, the ImageNet Challenge, by using deep convolutional neural networks. Suddenly, computers were recognizing cats versus dogs and hundreds of other object types with unprecedented accuracy. The key was training on massive labeled datasets, basically showing the network millions of images and adjusting internal parameters, weights, gradually until it got the classifications right. It was as if the code learned vision. Rapidly, deep learning was applied to voice recognition, hence Siri, Alexa understand you. Machine translation, Google Translate's quality leap around 2016 was due to neural networks. And more. One surprising, almost spooky ability of these networks is that sometimes they develop their own internal representations. For example, a neural translation system by Google in 2016 started translating between language pairs it had never been explicitly trained on. It had formed an interlingua, a hidden layer representation of meaning that transcended specific languages. It essentially invented its own internal language to bridge, say, Japanese to Korean via some abstraction. That wasn't hard-coded, it emerged from the learning process. We are witnessing code that organizes itself in ways even its creators might not fully pass. Segment 3, when AI amazes, creativity and game mastery. Go, an ancient board game vastly more complex than chess, was long considered a bastion of human intuition. Experts said it might be decades before AI could challenge top Go players. Then DeepMind's AlphaGo came along. In Game 2 of the AlphaGo vs Lee Sedol match, AlphaGo made a move number 37 that left commentators gasping. It placed a stone in a part of the board no human would normally consider at that stage. Not a tactical block or an obvious territory grab. One commentator said, "That's a very strange move. I thought it was a mistake." Lee Sedol walked out of the room, visibly flustered, and took nearly 15 minutes to respond. It turned out to be a brilliant play, something creative and new. AlphaGo went on to win that game and the series. An AI showing what appeared to be original creativity and strategic imagination, not just brute force. In fact, AlphaGo didn't brute force. It combined deep neural nets to evaluate board positions, much like intuition, with Monte Carlo tree search. It learned from millions of training games, both human and self-play, patterns of influence and subtle strategies. The move 37 was so unexpected that fans called it the Hand of God. Lee Sedol himself, after finally defeating AlphaGo, once in Game 4 with a brilliant, unlikely counter, his creative moment, said he never felt that amount of pressure, as if he were playing an entity that never errs. AlphaGo's victory was not just an AI milestone, it was almost philosophical. It taught us that AI can be both alien and inspired, finding solutions utterly different from human approaches, yet effective. We see AI, creativity in other domains too. Generative Adversarial Networks, GAN, a concept from 2014, pit two neural nets against each other. One generates images, the other critiques them, and as a result they produce astonishingly realistic outputs, from faces of people who don't exist to art and design patterns. AIs compose music now, in styles from classical to jazz. They write, admittedly mediocre poems. One AI even painted an artwork that sold at Christie's auction for $432,500, the portrait Edmond de Bellamy, 2018, using a GAN trained on historical portraits, effectively creating a new painting by learning the essence of artistic portraits. Did you know? In 2020, an AI language model called GPT-3 was released, with 175 billion parameters. Given a prompt, it can generate impressively coherent and diverse text, from essays to code snippets. It sometimes writes surprising things. Asked to write in the style of Shakespeare about a toaster, it can produce a pseudo-sonnet. Given half-written code, it can often complete it in a plausible way. It's not perfect and often makes factual errors or nonsensical statements. We call these hallucinations in AI, but the fluidity is a major leap from Eliza's day. It's trained on essentially a snapshot of the internet and digitized books, ingesting human knowledge and regurgitating patterns of it. This brings excitement and concern. Such AI can mimic human writing so well that it's hard to distinguish. Implications range from supercharging productivity, imagine your AI coworker drafting emails or summarizing reports, to worrisome misuse, AI-generated fake news or deepfake text. Segment 4. AI among us, helpers, colleagues, and sometimes opponents. Today, AI is embedded in daily life. Voice assistants use natural language processing NLP models to understand queries. The fact you can ask your phone, "Do I need an umbrella today?" and it replies in a conversational manner is thanks to massive language models and speech recognition nets trained on thousands of hours of audio. Recommendation systems on YouTube, Netflix, Spotify, etc. learn your preferences and those of similar users via matrix factorization and deep learning, serving up content eerily attuned to your tastes. Sometimes these algorithms surprise us by finding connections we wouldn't have, like an unknown indie song you end up loving, or a video on a hobby you didn't even know you were interested in. In medicine, AIs now assist in reading radiology scans, identifying tumours or fractures with high accuracy. They don't replace doctors, at least not yet, but act as a second pair of eyes that never get tired. During the COVID-19 pandemic, AI models analyse vast scientific literature to help researchers find relevant papers out of a deluge of information. In education, AI tutors personalise learning. If a student struggles with a math concept, the software adapts, giving extra practice on that specific concept, akin to a personal coach. Of course, AI also raises social and ethical questions. Biased data can lead to biased AI decisions. For instance, some early facial recognition systems had higher error rates on darker-skinned faces, owing to imbalanced training data. Or consider AI in judicial settings. Algorithms that predict recidivism might inadvertently reflect societal biases present in their training data. There was controversy around the Compass system used in some US courts. The phrase algorithmic bias is now in mainstream discussion. Essentially, code that learns from us can also learn our prejudices unless carefully checked. And let's not forget the moments when AI goes off script in amusing ways. Microsoft's Tay chatbot in 2016 is an infamous example. It was released on Twitter to learn from interacting with users. Within 24 hours, trolls had taught Tay to spew racist and offensive remarks, forcing Microsoft to shut it down and apologise. A case of machine learning gone wrong, illustrating that AI often naively mirrors the data it's given, for better or worse. From the daydreams of early pioneers to the reality of today's self-driving cars and talking fridges, the journey of artificial minds has been unpredictable and thrilling. We've seen AI master games, create art, augment our skills, and sometimes frighten us with its odd quirks or potent capabilities. The code behind AI has evolved from simple if-else expert systems to complex multi-million neuron networks that we train, rather than explicitly program. In a sense, we've written code that writes its own rules through learning. That's a fundamental shift in how we think about programming. It's less like instructing a robot and more like raising a child, providing guidance and examples and hoping it generalizes well. What's next for AI? Many foresee artificial general intelligence, AGI, on the horizon, a machine that can understand or learn any intellectual task a human can, blending flexibility with skill. Others remain skeptical of timelines, but one thing is certain. AI is increasingly our partner in nearly every domain, and its code, those weights and layers and data loops, truly change the world. In the next episode, we take a darker turn. When code goes rogue, viruses, hacks, and digital disasters. We'll delve into the underbelly of code, the malware, the cyber attacks, the software failures with catastrophic outcomes. Don't miss these cautionary tales of coding gone wrong.